Right, we are back and we'll continue with our discussion. If there's anything anybody wants to say, please do so now. Please speak, people. All right. So now we have said that many times we have a combination of static and dynamic quenching. What that means is shown nicely in this figure. Part of the quenchers, part of the fluorophores are engaged in forming complexes with quenchers, but there are free fluorophores as well that get excited, and other quencher molecules come and yes. Okay. Was that a question? Maybe not. Okay. And then this fraction can get dynamically quenched as well. And as we know, this Kd is given by Kq multiplied by tau 0. Now, how do we handle a situation like this? We have shown you the result first, that the Stern-Malmer plot in such cases is not linear, it is curved, and it shows an upward deviation from the straight line. If you plot tau 0 by tau, however, you do get a straight line. And from there, we should be able to get Kq. Okay. So we'll start writing like this. If I want to write I by I0, what is that? The fraction of fluorescence intensity that is retained at quencher concentration. The denominator is the fluorescence intensity in absence of quencher. The numerator is the fluorescence intensity that is seen in the presence of the quencher. If there was only dynamic quenching, then we would have got I by I0 equal to 1 divided by 1 plus Kd multiplied by Q1. What I've done is that I've just taken reciprocal of the Stern-Malmer equation for the dynamic quenching. However, we are not going to get so much of intensity at, if static quenching is also present, right? We'll only get a fraction of that intensity. That fraction is given by F. So our job at hand is to work out what is F. F is the fraction of molecules that remains uncomplexed in the ground state. Only this fraction is going to contribute to dynamic quenching, right? And whatever is complex is not fluorescent anymore. That is removed anyway. So only this fraction is going to contribute to fluorescence intensity itself. How do we do it? Well, we invoke the equation we had got for the static quenching case. And here, remember, we are dealing with concentrations. F naught divided by concentration of F is given by 1 plus Ks multiplied by Q. What is F? F is simply the reciprocal of it. Concentration of F divided by F naught. So that is given by then 1 by 1 plus Ks multiplied by a concentration of Q. Plug it in to the expression for I by I0. This is what we get. Take a reciprocal. We get sort of a modified, it is something that looks like a Stern-Malmer equation, because left hand side is I0 by I, but right hand side is a little more complicated. 1 plus Ks multiplied by Q concentration plus 1 plus Kd multiplied by Q concentration. Expand that. Since we don't have too much of time left, I'll not ask you to do it now. I'll just show you the answer. It's fairly simple. You get this kind of an expression. I naught by I equal to 1 plus Ks plus Kd multiplied by concentration of Q plus Ks multiplied by Kd multiplied by square of concentration of Q. Quadratic kind of term, right? So I can, there's nothing more that I need to do, honestly. What I can do is I can plot this I0 by I, I can take this I0 by I versus Q concentration plot and fit it to this equation. But then it is always better if we can see whether we can make a straight line out of it. That is why we had made the semi-log plot for the fluorescence decays and all, right? So let us see if we can somehow write an equation which is linear. To do that, first of all, I take 1 from right hand side to the left hand side. I0 by I minus 1 is equal to Ks plus Kd multiplied by Q concentration plus Ks Kd multiplied by square of Q concentration. Remember, this concentration of Q is something that I am adding analytically, measure using a balance, laboratory balance. So I just divide throughout by Q concentration. On the left hand side, I get I0 by I minus 1, the whole thing divided by concentration of Q. On the right hand side, I get Ks plus Kd, that's a constant term, plus Ks plus Kd multiplied by Q concentration. Okay. So now that is a linear equation. It is just that Q concentration is there on both the sides, one in the numerator, one in denominator. That's hardly a problem. So now when we plot this left hand side is called K apparent. This K apparent is given by I0 by I minus 1 divided by concentration of Q. When you plot it against concentration of Q, you get a straight line. Now from the slope, you get Kd into Ks. From the intercept, you get Kd plus Ks. So two equations, two unknowns, you can get Kd and Ks. But now I have a question for you. How do I know what is Kd, which one is Kd and which one is Ks? If you have two equations like this, we'll get two values, fine. But how do we know which one to call Kd, which one to call Ks? Any answer? Durjoy, what do you think?
Sorry, sir, I am not understanding how can I say that?
You're not understanding what?
How can I say that which one is KD and?
That's fine, but you have understood what we have discussed, right?
Yes.
Don't scare me, Baba. You start off saying I'm not understanding. Understanding is the present continuous tense. I get scared. Pratibha, you want to try?
No, sir.
Shishandu, is there any way by which I can determine KD? And the answer is there on the slide in front of you.
Yes, we can substitute. Sorry.
Right.
We can substitute K. We can substitute the slope by KD in KD plus Ks.
No, slope is KD into Ks. Intercept is KD plus Ks. I solve it, I'll get something, but then instead of KD into Ks, if I write Ks into KD, I'll get the opposite answer. Yeah, Himanshu, go ahead.
Sir, I think sir tan theta is equal to KD into Ks.
No, I'll tell you the answer. As I said, the answer is there in the slide. We also make another Stern-Böhmer plot with tau 0 by tau. Remember, tau 0 by tau, that plot gives us signature of only dynamic quenching. Yeah. So from that plot, we get to know what is KD. Okay. That is why we like time resolved measurement so much. That gives us the complete picture. So from the plot of tau 0 by tau versus Q concentration, you get KD, and then you work out both the time constants. Right. Let me show you an example of static and dynamic quenching. This is another paper. You can see what the name is. This is the dye, coumarin 102. And how does it fluorescence get quenched by different nucleotides, uridine and deoxycytosine. That is the study. Why that is important? If you want to know that, you need to read this paper. And papers like this, but in recent times, would be good candidates for your term paper. So what we see is that DC means deoxycytosine. For deoxycytosine, the plots of I0 by I and tau 0 by tau are coincident, which means it is completely static quenching in nature. In case of quenching by uridine, however, the plots of I0 by I and tau 0 by tau are different. And if you look carefully, the plot of I0 by I versus uridine concentration is not linear. There is a slight upward curve. Right? So from this data, one can work out by plotting Kap against the nucleotide concentration. See, in the case of BC, deoxycytosine, both the Ks have come out to be same. Well, K is equal to Kd only. That turns out to be 8 per molar. And in case of uridine, slope gives us the value of the slope is 158 m to the power minus 2. The value of the intercept is 25.6 per molar. From there, you find out what is Kd and what is Ks. And how do you know that Kd is 15.2 and not Ks? That you know from this tau 0 by tau plot. This is an example where you see static as well as dynamic quenching, and we learn how to make out between the two. Great. Next, we want to talk about quenching sphere of action, but I think we'll do it next day, because in any case, we have covered lots of ground today. I've uploaded all the slides anyway. So you are welcome to read this quenching sphere of action and the other part by yourself. On Thursday, we are going to complete our discussion of quenching. We have a couple of more topics to discuss here. And then we'll go on to discuss solvent effect on fluorescence properties, especially for charge transfer. Okay. So until then, I take your leave. Stay safe, stay healthy, and please do stay updated. Thank you.
Thank you, sir.